This video is about the concept of multi-level paging in operating system. So it is given that the virtual address is 32 bits and page size is 4 KB. So if the virtual address is 32 bits, then the virtual address space will be 2 to the power 32. And if we know that the size of virtual address space and a page size, then we can easily calculate the number of pages by dividing the virtual address space by the page size. So here the whole virtual address space is 2 to the power 32 and one page size is 4 KB. So the total number of pages are 1 M or 1 million, or you can say 1 mega. Let me erase that first. So in normal paging, you can say that is the three-step process. Paging is a three-step process. Dividing the address space into pages, storing the required pages in the frames of memory, and accessing the pages through page table. Multi-level paging means paging in page table. Let me explain it clearly. So, like normal paging technique, at first we have to load the required pages. Suppose the virtual address space has 1 million pages, but in those 1 million pages we just only this code section, data section, and stack section pages. So first we have to load that pages into the main memory frames or physical address space randomly. Like page 1 is located in the frame 0, page 2 is located in the frame 1, in this manner. For now, ignore the So for now, ignore the red ink part. Okay. So first we have to load the pages of virtual address space to the physical address space. And to access the physical address space, we need a page table. Okay. So suppose the in physical address space, page 1 is located in frame 0, page 0 is located in frame 1. And also in the page table, the frame 1 in page 0, frame 0 in page 1, like this manner. Okay. So the number of page table entries are equals to the number of pages in virtual address space. Okay. So the virtual address space has 1 million pages. So the number of page table entries are 1 million. Okay. Now suppose, let me erase it first. So now assume that the size of page table entry is 4 byte, and the numbers of 1 million, same as the number of pages in virtual address space. So if the size of one page table entry is 4 byte, then the total page table size will be 4 megabyte. That is very big. And one page table should fit in one page or one frame, as page size equals to frame size. Then so one page table should be fit in one frame. Okay. And one frame size is how much? One frame is 4 KB and the page table size is 4 MB. So the page table is bigger than the one frame size. Okay. So now we have to divide the page table into chunks. Means we have to repeat the same steps, like divide the address space into pages, storing the required pages in the frame, and accessing the page through a page table. We have to repeat these three steps recursively to the page table. Means we have to do simple paging to the page table itself. Okay. So now if we so if we divide the page table, we know that page size is 4 KB and page table entry size is 4 byte. So if we divide 4 KB by 4 byte, the result will be 1K. Means one page can store 1K or 1024 entries of page table. So one chunk size should be 1K. And the number of chunks, how much? If the total page table size is 1M, like this page table size is 1M or 1 million, or you can say 1 mega, and one chunk size is 1K, then the total number of chunks are how much? we have to divide the page table size by the chunk size. Okay, so the page table size is 1 m and the chunk size is 1k. So the number of chunks is also 1k or 1024. Okay, so let me remove this first. Now suppose, for your understanding purpose, suppose that suppose this is your virtual address. Just assume for understanding purpose, this is your virtual address space. And suppose this is a chunk, this is a chunk, this is a chunk. There are lots of other chunks also available in the page table, but these are allocated, okay, and the remaining all other chunks are unallocated. So at first we have to load these pages. We have to first name these pages. Like the first chunk we named as P0, the second chunk we name as PE, and the third chunk we name as PX. Okay, so now again we have to repeat the same process. So we have to load the pages of page table to the physical address space. Like the pages of page table are P0 and PX. So we have to load that into the physical address space. So suppose in the physical address space, page 0 is located at frame G, page is located at frame H, and page X is located at frame O. Okay. To access the pages of page table in the physical address space, this page. To access these pages, we want another page table. So the first page table is called as inner page table, and the second or last page table is called outer page table. Okay. So the number of page table entries in outer page table is equal to the number of pages, and the number of pages in inner page table is how much? 1. So the number of entries in outer page table, this is one entry, this is second entry, this is third entry. The number of entries in outer page table is 1. And previously we assumed that page table entry size is 4 bytes. So now the outer page table size or the size of whole outer page table is 4 byte into 1k is equal to 4 KB. Now, now the outer page table size is 4, and in the question it is given that the page size is also 4 KB. So one outer page table can easily fit in one frame because the frame size is always equals to the page size. So in this way we can decrease the size of page table. It is one of the purpose of multi-level page.